Sydney.
And I'm Renee.
And we will be discussing floating plates today.
Our topic question is, how do the plates move?
We broke that question down into 3 testable questions.
What evidence do we have that tectonic plates are moving?
What are the densities of the components within the lithosphere?
What features would you find at each of the 3 types of plate boundaries? Our first question is, what evidence do we have that tectonic plates are moving? There is fossil and geological evidence that support the claim that a long time ago, the continents were connected in one giant landmass. You can see that the east coast of South America and the west coast of Africa fit together like one giant puzzle. The fossil record shows that these animals and plants lived together at the same time, but on different continents. This only makes sense if the continents were connected. This white area shows where glaciers have scarred the rocks of different continents. This only makes sense if the continents were a giant landmass, because some of these glacier scars are in areas that are at the equator where the climate would not support glaciers to be formed. This map shows the Appalachian Mountains in North America and the Caledonian Mountains in Europe. These mountains are made of the same types of rock, and the rocks are of the same age. However, they are separated by the Atlantic Ocean, and there is no mountain range underneath the ocean that separates them. This indicates that when these mountains were formed, the continents were connected. Another piece of evidence is that if the continents and the oceans were in their same position and shape as they are now, the sediment on the bottom of the ocean would be collected uniformly. However, it is thinner in the center and thicker along the edges. This indicates that sediment hasn't been collecting as long in the center. This brings to mind a question: why is the seafloor younger in the mid-Atlantic? Another question is, what did the Earth look like a long time ago when the continents were connected?
The second researchable question we had was, what are the densities of the components of the lithosphere? Our claim is that the lithosphere is made up of 3 distinct pieces, and each piece has a unique density. This density jar picture here can be representative of those 3 pieces. The clear liquid would be the crust that makes up the continents. It's made of granite and other sedimentary rocks. It's the least dense, so it'll be on top. The blue liquid represents the oceanic crust, which was made up of basalt and igneous rocks. So it is more dense than the crustal material, but less dense than the mantle, so it is in between. The red section would be the upper mantle, which is a rigid part of the mantle made of peridotite, and it is the most dense, so it lies on the bottom. An actual diagram of the lithosphere is as such. So the gray section here would be the continental crust. The orange section is the oceanic crust, and if those 2 crusts were to collide, the oceanic crust would subduct under the continental crust, but it wouldn't go all the way through to the molten mantle because the peridotite is more dense, so it'll slide under and lay in between. A couple questions that we came up with after researching this question are, what would happen to the densities within the lithosphere during convection, and what does convection do to the densities within the mantle? Our third and final testable question that we researched was, what features are found at each of the 3 types of boundaries? Our claim is that the interactions between moving plates is what shapes the Earth. Our first boundary is the convergent boundary. There are 3 types of convergent boundaries, where an oceanic crust and an oceanic crust collide, a continental crust and an oceanic crust collide. At this level, your oceanic crust, which is more dense, would subduct. Your continental crust would go up, and you would form a trench because of the subduction. And our third type is going to be continental and continental. because they're the same densities, they're going to come together and neither one's going to want to subduct, so they're going to push up and create a mountain range. A real life example of that kind of convergent boundary is going to be the Himalayan mountains, where the Indian crust and the China crust is going to collide, and it's going to make one of the tallest mountain ranges in the world. Our second boundary is the divergent boundary. That is where two plates are going to separate from each other, and new mantle material that is hot and less dense is going to come up and create new crust. And an example of that is the Mid-Atlantic Ridge. Like Renee was talking about earlier, you have new, thinner crust here in the middle and old, denser, thicker crust out at the edges, and that's because the new hot materials coming up, creating crust and pushing that old stuff away. And our last but not least boundary type is going to be a transform boundary. That's where two plates will slide past each other, and at those plate interactions you get a lot of earthquakes because of the friction. And one of the most famous areas that you see that is the San Andreas Fault in California, and you can see that the outside of the continent is moving forward while the inner part is moving down. That's what causes those earthquakes and that crack there at the San Andreas Fault. A couple questions we came up with during the section that we researched were, why are the Himalayan mountains the tallest? And does oceanic crust get pushed by the new material, or is oceanic crust being pulled because it's subducting and becoming more dense because it's cooled?
Started with the question of how do the tectonic plates move? This led us to three researchable and testable questions. The first is, what evidence do we have that tectonic plates are moving? This led us to another question: what did the Earth look like a long time ago when the continents were connected? And why is the seafloor younger in the mid-Atlantic Ocean? Our second question is, what features would you find at each type of plate boundary? This led us to the question of, why is the Himalayan mountains the tallest? And is the oceanic crust being pushed or pulled?
Our final question that we researched was, what are the densities within the components of the lithosphere? Two questions we came up with after researching that are, how do the different densities in the lithosphere react to convection, and how does convection itself affect the densities in the mantle? Well, I hope we have explained why plates are floating, and see you later.